Hello everybody, so this is again Dr. Sergey Sargasov, and today we are going to learn how to graph rather challenging polynomials. So let me show you specifically this example here. Ready? Let's graph the polynomial. We'll learn how to do this in the process. So graph the polynomial, polynomial function p of x, f of x or p of x is equal to, ready? Let's say we have let's do negative x to the sixth, okay, plus a 5x to the fourth, and minus a 4x squared. All right, let's see, what can we do with this thing, right? That's a 6th degree polynomial, right? What does it mean, 6th degree polynomial? That means that the degree, that's really the kind of the defining of the whole pattern of the polynomial, right? When we talk about, let's say, just this term, then it's going to be a parabola. It's going to be some kind of x squared, right? That's going to be the dominant term. But then if we have this, it's a quartic, right? If we had just an x, that would be a linear. It would have to be a line. So the highest degree, right? That's 6. It's called the degree of the polynomial, the highest power term. The leading coefficient is a -1, right? In fact, let's look at this. Let us look at something called end behavior. What happens on the ends, right? When you get big numbers, or small numbers, very negative, very positive, what happens? If it goes very big, or very small, this is the dominant term. Think about it. If I put 1,000 in, right? 1,000 to the 6th power is way bigger than 5 times 10, or 1,000 to the 4th power. This is going to be by 1,000,000, by order of magnitude of 6, 10 to the 6th bigger. Just this term than that one if you're doing 1,000 for x. So you go that way, these are negligible. Go this way, these are negligible. So let's look at this. The leading term, an x to the n, is equal to, this is the leading term, it's a leading term of the polynomial, is equal to the negative, right? And it's like a -1, x to the 6th. The an, which is the leading coefficient, right? It's equal to -1, which is less than 0. It's a very important thing for us. And degree is n, is 6, right? N is equal to 6. It's an even degree. And what did we talk about earlier in the class? That when you have an even degree, whether it's an x squared or x to the 4th, it's going like this. Up on the ends, or maybe down if you flipped it, if you have a negative leading coefficient, which we do. Remember, the graph transforms of a negative flipping around the x-axis. So here's what happens. It goes like this to that, and behavior looks like, and behavior, which is very important for us, right? It's half of kind of the way to graph this thing, or sketch it at least. And behavior would be like this, pictorially, so left up and right up. That's if we had a positive. So no, actually what happens is, then behavior would be this, but flipped. So it would become, let's flip this around, and what happens is, it would become actually left down, right down. That's the one we care about. Okay, so even, yes, but then we have the negative giving us this, not that. Okay? So now let's look at this as follows. Can we factor this thing? Can we find, the x-intercepts? They're also called the zeros of this polynomial, right? To do that, let me show you how we can do that. Well, we can see there's something in each of those terms for sure. First of all, take out a negative, right? So we can say, p of x is, take out a negative, and then also, because I want to make a positive something there, right? And then, what about an x squared everywhere, right? Take out a negative x squared, and you see what happens. You have x to the 4th remaining, and that does give us a negative x to the 6th. This divided by negative x squared is a minus of 5x squared. If you multiply this way, that's you get a plus 5x to the 4th. And then this is going to become, finally, just a plus 4, right? And if you can notice a pattern in this, this will also factor somewhat. Watch this. It's a negative x squared times, and let's just pretend, instead of x and x like we usually factor, let's do an x squared and an x squared. That will give us, the first terms will be giving us x to the 4th. Now the last terms better give us a positive 4 with a negative 5x squared in the middle, so we need a minus for sure, remember because plus and minus. And how do I get a 4 and a 1, or a 2 and a 2 giving us a 5? How about a 4, a 1, and a 4, right? That does work out. Negative 4x squared minus x squared is a negative 5x squared. Cool, right? So, does anybody know the difference of squares?
So
No worries. Anybody know the difference of squares, right? Where we have this is ax squared minus bx squared is what? You can factor this as follows. Now, remember the trick that we do? Let me show you a quick trick. If you ever have a plus b times a minus b, what happens? That's going to be the first terms. Remember the FOIL method, first, outer, inner, last? The first terms, a squared. The outer terms, the o, right? Negative ab. The inner terms, plus a ba or ab, doesn't matter. It's a commutative property. These are the same as these, right? Commutative property of multiplication. And the last terms, negative b squared. This is ultimately, these go away, a squared minus b squared. And what I tell my students sometimes, what I tell you guys, is the following. Here's a trick. For example, you give me a number, I don't know, 42. I multiply it by, let's say, 38, and I get 1596, 1,596. Really? All right, another number. 71, all right, 71. Let's do times 69. Oh, that's 4,899. And this is how am I doing this so quickly? And try to figure this out yourselves. How am I doing this so quickly? I'm doing it this quickly because I know, let me show you. This is 40 plus 2 times 40 minus 2. I saw that, right? And if you have that trick, actually my grandmother taught me this trick a long time ago, right? And so many years ago, so this is 40 squared minus a 2 squared, and that is exactly, right? That's going to be 1,600 minus a 4. So the hardest part for me there was taking a 4 away from 1,600, and so ultimately this is the same thing, where it's going to be 70 squared minus a 1 squared, 4900, right? Minus a 1 does give us this. Cool, right? Just for fun, a few numbers where you can kind of show these tricks off to, your either students or children or, peers or colleagues, whatever, right? Anyway, that's a little trick. We're going to rush and finish this polynomial with the time we have left, about 5 more minutes. Let's do this. The difference of squares trick here is that, yes, it's a minus, copy this, x squared. And this is x, you can do x plus 1, x minus 1, right? X squared minus 1 squared. And this is x, what do you think? X plus 2, exactly, and then x minus 2, all right? And so what we have here is we have zeros, things that will make this 0, and then multiplicities. Multiplicities spelled like this, okay? And so what happens is, okay, what is a 0 for this? This is a 2, makes it 0. What about this term? It's like x minus 0, really. X squared, what makes it 0? Put a 0 in. Multiplicity, 2. Put a negative 1 in for this. Multiplicity, just one of them, right? One factor, 1. 1, multiplicity, 1. How many of them are there? Multiplicity, how many of these factors? X plus 2, there's only one x plus 2. So negative 2 makes it 0, and there's one time. And x minus 2, so again, a 2, and multiplicity is 1. When it's an even multiplicity, this is even. These are all odd. 1 is odd. This multiplicity is odd. And this multiplicity is odd. When it's an even one, it touches the x-axis. You'll see like a parabola, x squared. It touches. Whereas the 1, it crosses like a line, right? So touch at the origin, 0, 0, because that's the 0 is like the x-intercept, right? Odd, it crosses at negative 1, 0 x-intercept. Odd, it crosses at the 1, 0 x-intercept. Negative 2, 0, so it crosses there. Cross at negative 2, 0. And what do you think this happens? Cross at 2, 0. Let's see what we can do with this end behavior and this zeros multiplicities, the x-intercepts and what we know happens at them. And these are the only locations, this 5 spots where it will touch the x-axis. Because if you had another spot, what would happen? You would have another 0, and nothing else besides 0, negative 1, 1, negative 2, and 2 can make the 0. If you put a 3 in, I know not 0 all the way through, it's not going to be 0. Has to be something has to be 0 by the 0 product property, right? So let's finalize this graph as follows. We go, again, this is kind of a symmetric one in a sense. And if you think about it, this is an even function. If you put a negative something and a positive something, they'll just be the same, ultimately the same things, because x to the 6th plus or minus is going to give you the positive still. X to the 4th plus or minus is going to be positive, same thing, and and that's the same thing. So if you put a negative x and an x, you'll get the same thing. This is an even function. We better have symmetry around the y-axis. So let's try this. Let's do the x-intercepts. That's what I would start with. Negative 2, negative 1, 0, 1, 2. Let's go left 2. Let's go left 1, negative 1, 0, 1. Let's label it this way, and 2. Okay? If you were looking for the y-intercept, well, that's what it is. You put a 0 in for x, and it's 0. It's an origin, right? There's only one y-intercept. It's a function. Now, it's going down left and down right Let's make sure that happens. This is the last x-intercept on the left, the last x-intercept on the right. All right, it does it cross? It crosses here, right? And it crosses everywhere besides the 0 where it touches. Let's cross. We cross. Probably not so a little shallower, a lot shallower here. If you graph it on a graphing calculator, you'll see it'll probably be something more like this, and then we touch, 0, 0, we touch. You see that? Kind of cool, right? And then it's even, it's symmetric. We should copy this kind of same pattern on the right side. And I encourage you to check out on the graphing calculator and see how close are we to getting the actual graph of this function. There's a polynomial graphing for you in a nutshell. Again, I know this is a rushed kind of a demonstration with the time we have. All right, I wish everybody the best. Have a great day. And if you have any more questions, comment on what you have seen and what you liked and what you didn't. Okay? All right, thanks.